Yo, what is up, everyone? Episode 99 today. Yeah. So episode 99 today. Probably gonna be a little bit of a shorter video. I'm heading up to Chicago, so maybe we'll just put in a couple problems here. Maybe be about an hour long, or maybe a little bit over an hour. I gotta pack my bag and get out of here. It's about a 3-hour drive, so yeah, we're gonna take a look at a few problems. So let's take a look. Oh, I thought we had two some today, bro. That would have been crazy. Anyway, probably continue the rest of our Leetcode. Probably do this one. Maybe do the problem of the day, and maybe another problem, and then we'll call it. But yeah, let's take a look at our Pokemon of the day. Right, so Pokemon 99 today. We got a Kingler, the evolution of Krabby. Let's check out the sound, shall we?
Yeah, Ash did it. Krabby did a great job.
There we go, he's evolving.
Oh no!
Huh? Krabby evolved! Huh? Krabby
Hang on, bro. Cookie. There you go. There's our sound of the day. Do it one more time. Cookie. Let's hear it one more time. It's pretty much the same as yesterday, but yeah. That's our sound of the day. Let's take a look at our motivational quotes. Let's take a read over here. 200 motivational quotes to inspire you. The road to success and the road to failure are almost exactly the same. There we go. Our quote of the day. Road to success. The road to success and the road to failure are almost the exact same. That was a crazy. All right, let's take a look at our problem today. We got a count and say problem 38. The run length encoding RLE is a string compression method that works by replacing the consecutive identical repeated 2 or more times with a concatenation of the character and the number making the count of the characters. Bro, what does that mean? Sequence of digit strings defined by the recursive formula. Count and say 1 is equal to 1. Count and say n is the run length of count and say n minus 1. Bro, I have no idea what any of this means. Go practice some more valuable questions. Two, 3, 2, 1, 1, 4, 5, 1, 2. Create another helper function that takes the array of pairs and creates a new integer. For example, if you call 2, 2, 22, 3, 2, 23, plus 1, 1, 4, 5, 54, plus 21, equal Now with the two helper functions, you can start with 1 and call the two functions alternatively n minus 1 times. Okay. Okay, let's create a helper method. Let's call it create a helper function that maps an integer. But what are we given? We're given, for example, if you call this function, they only give us I'm a little freaking confused, to be honest. Let's watch a Leetcode video on it, because I'm not... Did he make one yet? He has not. Sometimes he doesn't make the videos, bro, I swear, like...
Supercharge your most demanding HPC and hyperscale data center workloads with the NVIDIA H200 NVL and NVIDIA H100 NVL GPUs. First, the NVIDIA H200 and
Hi, how's it going? Welcome to Code with Z. Today's question is Leetcode number 38, count and say. Now I want you to know that I'll explain and visualize everything in the coming slides, but for the sake of reading the question, let's see what the question is actually asking us for. So as we can see, here the description vaguely says that the count and say sequence is a sequence of digit strings defined by the recursive formula, and the recursive formula is that the count and say of 1 is gonna be equal to 1, and the count and say of n is gonna be equal to the run length encoding of count and say of n minus 1. Now, what does this even mean? Well, let's first of all understand what run length encoding means. As you can see, we're given an example here about run length encoding. Here we have this number here, and the description tells us that we're gonna replace 33 with 2 and 3. Why? Well, if we actually check here, we have 2 occurrences of 3. And this number here is representing the number of occurrences of the number next to it. For example, we have 33, we have 2 3s, the number 3 was repeated 2 times, and that's why we have 2 here, and this is the number that was repeated. So we have 2 occurrences of the number 3. If we check our other example, here we have 222, right? This was replaced by 3 and 2. Why? Because we have 3 occurrences of 2, and the number itself is 2. That's why we get 3 and 2. Then we're gonna replace this 5 with 1 and 5 because we have 1 occurrence of 5, and then we're gonna replace this one with 1 and 1 because we have 1 occurrence of the number 1. Now you get the idea, but this was the example for our run length encoding. not the count and say example itself. If we check the example for our count and say, as I said, this question.
Oh, okay, I understand. I understand. Okay, so we start off with 4, right? So our 1 will always be, will return 1, right? Then we have 1 of 1, 1. So that's how we get here. Then we have 2 of 1. That's how it gets here, right? That's number 3. And then 4, we have 2 of 1 is, what is 2 of 1? We have 1 of 21.
Is a little bit vague, but don't worry, I'll explain and visualize everything in the slides. Here our input is actually a number like 4, and we gotta return this. Now why is 4 equal to this number here? I'm glad you asked. Let's break this down. So why should 4 be equal to this number here? If you remember in the description, it said that the count and say of 1 is gonna be equal to 1. Now why do we need this? We have 4, not 1 here, right? Correct, but the count and say of 2 is equal to 1 and 1. Why? Because when we actually count the count and say of 2, we're gonna look at the previous result and we're gonna be like, how many occurrences of this number do we have here? Well, we have 1 occurrence of the number 1. So 1 occurrence of the number 1. Then we're gonna calculate n of 3 and we're gonna say n of 3 is gonna be equal to, well, let's check our previous answer. Here we have 2 occurrences of the number 1. So n of 3 is gonna be 2, 1. Again, 2 because we have 2 occurrences of the number 1 and this is the number 1 itself. Now, when we want to calculate n of 4, we're gonna be like, alright, let's check the previous answer. We have 2 and 1. We have 1 occurrence of the number 2 and then 1 occurrence of the number 1. So n of 4 should be equal to 1, 2, 1, 1. Why? Because we have 1 occurrence of the number 2 and 1 occurrence of the number 1. And this is why n equaling to 4 is equal to 1, 2, 1, 1. This is how we solve this problem. For example, if our n is equal to 6, we're gonna start from 1 all the way till 6 so we can see what 6 should be actually equal to. Now, we're gonna need a function that's gonna do this calculation for us, meaning we're gonna need a function that's gonna tell us how many occurrences of each number we have. And to be honest with you, this is the most important part, because if we check, we're literally calling this function over and over again. Each time we're gonna be like, how many occurrences of each number do we have? And we're just gonna keep on calling it for the next round and the next round. So let's first define this function that's gonna calculate how many occurrences of each number we have. Alright, so let's say we have a string of numbers and we wanna see how many occurrences of each number inside of this string exist.
ChatGPT can now create website wireframes. With our new custom GPT, we guide you through.
Well, we're gonna need a result variable. Do you agree with me? Because we have to return something, right? And because we have a string and we gotta see how many occurrences of each number exists in this string, I think we can all agree that we're gonna need a loop to loop through each one of these numbers. So we're gonna be like, we're gonna have an I variable and then we're gonna have a loop. This is gonna be representing our loop and anything inside of this is gonna be inside of this loop. Here we're gonna ask ourselves, so what are we doing inside of this loop? Well, we wanna count how many occurrences of each number we have. Alright then let's define a count variable and let's
Just call it backtrack. We pass in n. Right? Okay, we probably want to pass in our n. I want to pass in our I, our index, and then our cool backtrack n index 0. Okay, let's just leave it like that for now, right? So our base case, right? If n is equal to 0, we will return 1. Backtrack. I guess we need like some sort of cur as well, right? For our string. Well, if I is equal to 0, we want to return bro. Honestly, I'm not sure.
Initialize it to 1 because if we have a number, the minimum occurrences it can have is 1, right? And then we're gonna be like, if we only had one occurrence of one number, we're gonna be like, result should be equal to result plus count plus the number itself. Meaning, for example, if we have the number 7, we're gonna be like, we have one occurrence of the number 7, so 1 here, plus the number 7 itself. It makes sense, right? We're saying result should be equal to result plus the count of the occurrence, and next to it we're gonna have the number itself. This is literally the current number that we're gonna be looping through inside of our loop, and this is the count of that number. So if we have 7, we're gonna be like, we have 1 here of 7. And then to not get stuck inside of an infinite loop, we're gonna be like I++, right? This makes sense. And then at the end, we're gonna return our result. Simple as that. Now, what if we have more than one occurrence of each number? Because currently we're saying that we only have one occurrence of each number, and this is it. But what if we have like 3 7s next to each other? Well, we gotta count that. So we're gonna be like, all right, let's add another loop, and this is gonna be a tiny simple loop. We're gonna say we're gonna stay inside of this loop if the current number that we have is equal to the number next to it. For example, if we have 2 7s next to each other, that means the current number is equal to the number next to it. So we want to actually increment our count to make sure that we add the correct count here after we're done with our loop, and we want to increment our I so we make sure that we loop through the numbers correctly. And believe it or not, this is our algorithm. It's that simple. We literally have a result, and then we have this loop, and we're going to be like, all right, we need to calculate our count, so let's define a count variable here, and then we're going to keep on looping inside of this other loop if the current number is equal to the number next to it. If not, we're just going to ignore all of this loop, and we're going to be like, result should be equal to result plus the count of that number and plus that number itself. Then we're going to increment I to keep on looping, and we're going to return result. But if you remember, our input was something like 4, right? And if we feed 4 to this algorithm, it's going to return 1 4. Why? Because we only have one occurrence of the number 4. But as you saw in the first slide, this is how we should actually calculate the sequence of our n. Now currently we have this function that's going to tell us how many occurrences of each number that we have. For example, if we feed this to this function here, meaning if our s was equal to this function will return 1 2 1 1 because we have one occurrence of 2, so 1 2, and one occurrence of the number 1, so 1 1. So all we need to do is to call this function from n equaling to 1 all the way till n is equal to the number that we were given. Now, how are we gonna do that? Well, let me show you in the code. Let's code this in the simplest way possible. Alrighty, so first of all, let's define the function that's gonna calculate the number of occurrences of each number inside of our string. So we're gonna call it next sequence and it's gonna take in a string of numbers. And here we're gonna be like, this is gonna look really similar. We're gonna have a variable called result, and this is gonna be initialized to an empty string. Below this, we're gonna have a variable called I, just like we saw on the slides, and this is gonna be initialized to 0. Let me add a space here. And then below this, we're gonna have a while loop, and we're gonna say keep on looping as long as I is smaller than s.length. And then we're gonna enter this loop because we wanna keep on looping until we've checked all of the characters inside of our string. So we wanna keep on looping as long as I is smaller than the length of our string. Here we're gonna define a variable called count, and this is gonna be initialized to 1. And then we're gonna have our second loop, just like we saw on the slides. And we're gonna say keep on looping as long as s of I, meaning the current character, is equal to the character next to it. And we wanna keep on looping and increment count and I on each round. But for example, if we're at the last character of our string, we don't wanna check the character next to it because that's gonna be undefined. So here we're gonna be like, we wanna have this condition, but we also want to have this condition. First, check if I plus 1 is smaller than the s of length, meaning first of all check if we're not at the last character, because if we are at the last character, we don't want to check the character next to it because it's going to be undefined. And then below this, we're going to be like result should be equal to result plus count plus s of I. But if we check, we have to return a string here, and our count is initialized to a number. And the reason it's initialized to a number is because we want to calculate our increments here. But at the end, we got to return a string. So we're going to convert it into a string like so. And then we have to have I++ here, so we don't actually get stuck inside of an infinite loop. And then below this, we're going to return our result because it's filled with answers now because of our 2 loops here. Now, this is our next sequence function, and now we need to call it properly. Now, what do I mean by properly? Well, if we check here, our n is 4, and we start calling our count and say function from 1, and then 2, and then 3, and then 4. And the reason behind it, just like we saw on the slides, is because the answer of this one depends on the previous answer, and the answer of this one depends on the previous one, and this one depends on the previous one. But count and say of 1 is going to be always equal to this number, and this was given to us in the question itself. Count and say of 1 is going to be equal to the string version of 1. So we're going to use this to our advantage, and we're going to say, let's define a variable called current sequence, and this is outside of our next sequence function. As you can see, this is our next sequence function, and I'm defining this variable outside of it, and we're going to initialize it to 1. And this is going to be representing count and say of 1. So now we need to call our function here from the very beginning all the way till we reach the number n. So let's do that. We're gonna actually define a for loop. We're gonna say for let I being equal to 2, because we already have the answer for the first one. As you can see, we have it here. So for let I being equal to 2, we want to keep on looping as long as I is smaller than or equal to n, because we want to keep on calculating it until we reach the number n, and we want to keep on incrementing I on each round. Here we're gonna be like, let's call our function because it's gonna be filled with the
Just gonna look at some of the solutions. I'm not sure, bro. Dot. One line solution, no fucking way, dude. Bro, this is so sweaty, dude. How does someone come up with this shit? Like, return 1, string 1, right? Otherwise, we call our what we do here, we result is equal to this, count is equal to 1 for I in range 1 in length s. Bro, it's driving me insane, like. Man, it is. Oh. One return curve in range 2 n plus 1. Why does he do that? I do not like this problem, bro. Like, this is for sure. This is a really tough problem for me, bro. Like, really tough for me to think about this. Like, it's not a Friday sort of problem, bro. I'm gonna give up on this problem. I don't think I'm in the zone for that sort of problem. It's definitely a tough problem too, so let's take a look at palindrome partitioning. Given a string S, partition S, such that every substring of the partition is a palindrome. Return all possible palindrome partitioning of S. Given a string S, partition S, such that every substring of the partition is a palindrome. Return all possible palindrome partitioning of S. So how is this a palindrome? Like, what? Isn't it the same forwards and backwards? Palindrome is a string that reads the same forwards and backwards. Yeah. How does this read the same forwards and backwards? AAVVAA. Like what? This is a palindrome. How is AAB a palindrome, bro? Like, what? How is this test case? How? Oh. Bro, what is going on here? We'll be back in a second. AAAB, but why is B? Why is B twice? Each list is completely different partition of the original string A, B. The B is part of both the string ends in B. B palindrome, AA, B, AA palindrome, B palindrome. Okay, so I think here I'm confusing myself a little bit. I think what I do here is I create each backtrack and create each thing, right? And then I store it inside of A palindrome, A, B, AA. I'm still a little bit confused, but that's what I'm going to do for now, right? So I'm going to create a backtracking function. We're going to pass in our index and our cur, right? We're going to have some sort of res array over here. Okay, our base case is going to be, well, maybe we can have some sort of like is palindrome function that passes in cur and just returns if it is palindrome, right? So our base case can be like, well, if is palindrome cur, then we can just and we would append this res.append cur.copy, right? Return. Have our recursive case, and we go, okay, well, if length of cur is equal to 1, we would return true. Else if the length of cur is greater than 2, then we check, well, function. Can we just compare the end, right? Is that... if cur 0 does not equal, if cur 0 does not equal cur length of cur minus 1, then return false, otherwise return true. Jeez, man, this is such a stupid is palindrome function. No, we have to do, yeah, that's what I thought. 2 pointers, right? So, okay. So we have left is equal to 0, right is equal to the length of cur minus 1, right? And we do, well, if left is less than right. Yeah. If left is less than right, then sorry, we need a while loop first. While left is less than right, we check, well, if cur left does not equal cur right, we would simply return false, right? Otherwise, we would just increase our left pointer by 1, decrease our left pointer by 1. We would just return true, right? Okay, that's right. Okay. Alright, so this is our is palindrome function, right? We check is palindrome cur, then we append our copy, we return. Our recursive function would be, well, we need to loop through each thing, right? So we'd append cur.append, 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 shit, man. Append s index. Let me call our backtrack. Backtrack index cur incremental index +1. Then we pop. Then we would just return here. Return our res. Let's see what this gives us. We don't even call our backtracking function. Backtrack. We want 0, and then we want our cur, so it'll just be an empty string, empty array. Is that his palindrome correct? I guess this isn't stopping our looping, technically, right? Like, when do we actually stop the recursive function? Okay, base case is palindrome cur res open. Yes. If index is equal to the length of cur, res.append cur return. I just want to generate all the permutations, right? That's probably the first where we want to get. So let's comment all this shit. Why are we not generating any permutations? Why are we not generating anything? Why are you not generating anything? Oh shit. Okay. Length curve, we have to do length S. Now I think it'll generate. Okay, finally. Backtrack. Index +1. Okay. I'm not generating C. Why are we not? Oh no, okay. AAB, AA, AB, AAB, AB. So this is a permutation. This is a permutation. In this case here, if I was to run this, right, and then I ran this function here and checked if it's a permutation, right, it would say this one isn't a permutation. Sorry. Alright, let's do like, okay, if is palindrome cur pass in this stuff. See what it returns us. String out of range. Oh shit. hell is this shit? Okay, I need to get back into this. Okay, so you're treating Kerr as a string you are building, but the problem wants you to build a list of palindromic substrings that partition the entire string. But Kerr is a list of characters. I'm so confused, bro. I don't understand what that means, bro. Like, a string that you're building, but the problem wants you to build a list of palindromic substrings. Aren't these substrings that I'm building, bro? Isn't this a substring? Like, these palindrome curve. A curve is a list of characters, i.e. A, B, not a string like AA or AAB. Okay, so what they're doing here is same base case, right? Instead here, what is he doing? He's looping for end in range start +1, length s +1, substring s. I still really believe that I'm generating all substrings here. Like, these are all substrings, right? So stupid, like. AAB. So we have to grab each substring. Like, what? So when passing in star, if star is equal to length s, or it doesn't, right? Passing end here, right? It's +1. S, so we grab the substring. We slice here, Python, grab the substring. There we go. Okay. He checks if it's palindrome, right? But we do that. Do cur.append substring backtrack and cur.pop. It is palindrome cur. I'm gonna pop. Get rid of this. If index is like, bro, it is so cold in here, bro. Oh my god, dude. Oh my god, I'm checking the wrong thing here. Substring. Cur.append substring. This palindrome. Shit. Backtracking function. I just don't get this problem. Like, I don't get, like, what exactly is a substring, why it's exactly like this. I think it's like, bro. Why is this recursive function, bro? Oh, this is a recursive function. Bro. Jeez, man. Let's do a backtracking. One more backtracking problem. We'll call it a day. Difficulty. Let's do sort of by acceptance. Sums all parts, bro. Like. In 2 integers and k, return all possible combinations of k numbers chosen from 1 to n. You may return the answer in any order. Okay. Now 4 choose to 6 total combinations. 1 3 1 4 2 3 2 4 3 4. Okay, let's do, alright, create a res array, create a backtracking function where we pass in, we probably want an index, and we want, I guess some sort of cur, right? Track, let's do 0. What would be our base case? Well, what would be our base case? Combinations of k. So I guess it would be k, right? If our yes, if the length of cur is equal to k, then we would append cur and return, right? Our recursive case would be, well, starting from 1 to n, right? So we'd probably want to pass in 1. Right, so we would go, okay, well, probably need a for loop here or something. We go phi in range length n, phi in range, we'd go from start to n. First we'd want to do, okay, well, code.append, we want to append I, right? And we call our backtracking function and do, okay, well, let's call this start. And do start plus 1. Pass in our cur. And cur.pop. Let's return. I don't want to return. We would just return our current res. We don't want so we got this and we got 2 2, so there should be 1 4. We want to append 1 4 though. We don't want 2 2. Given two integers n and k, return all possible combinations of k numbers. I have to refresh myself on what a combination is. If I incur continue. That should skip the duplicates. 1 3. I guess like If I is greater than then cur. No, that's not gonna work. Kind of did it. Now we just need let's see if this works. I don't know. Yeah, no, does not work. You're always calling backtrack start +1, which means you're skipping potential valid values by not incrementing I. Jesus, dude. Oh my god, that was it. Fine, range start and +1 if. So apparently we don't need this either. Or do we? want to see the recursion tree just to be sure. Backtrack to that, pick 3. Oh man, some people, bro. Alright guys, I think I'm gonna call it there. I'm gonna start getting ready to drive up, so appreciate you guys watching, and I will see you on Monday for episode 100. See you guys on Monday.